Okay, this is the video for the entrance card. This is me, Dr. Soto. We're going to talk about integrating factor today. Um, in this particular problems, we're actually solving differential equations. The differential equation is actually down here. So we're looking for a function, y, such that when you multiply the derivative of y times x, you're going to get 2y plus x squared. And so that's actually right here, where if you notice, x times y, the derivative of y should be equal to 2 times y plus x squared. And so our goal is to find this function y, but notice we have a couple of other restrictions. X has to be positive. We'll see why that's important later. And then when we plug in 1 for x, we should get 7 for y. And so we're going to try to solve this. And this is sort of a trick. It's a very special trick that we'll talk more about in class. And it's very useful in many different areas in math. So let's go ahead and go over the trick and see if you kind of understand. So the idea is the following. First of all, this trick, the integrating factor trick, only works. So the integrating factor only works if the differential equation has the form and here we go. So it has to look like this. It has to be a derivative of a function. You're adding some other function, but this function is a function of x. Okay, this one's explicit. You'll actually be able to see it. Then you'll have this function times y, and then it'll equal to a different function, b of x. Usually b is different than a. It doesn't have to be, but usually they are different. And so this is, if the function looks like this, then we'll use integrating factor. But it has to have this form. So this is our first problem. Look at our function, look at our equation, our differential equation, it doesn't have this form. And so we have to do a little bit of algebra to see if it meets our expectations. And so here's the little bit of algebra that we do. So we have xy prime equals 2y plus x squared. And so the first thing I notice is that I need to move the 2y, so I need to move this 2y to the other side, to the left-hand side. So we do a little bit of algebra. We subtract 2y from both sides. And so now we get that xy prime minus 2y is equal to x squared, because these cancel right here. All right, so it almost looks like this form, right? At least I have a function, but at least I have the y prime over here, and I have the y over there, but the only problem is actually this x. This x is causing me a problem. So I'm going to have to do something about this. And so here's what we're going to do. We're going to do, again, more algebra. We're going to divide everything by x. So I'm going to multiply the left-hand side by 1 over x. I'm going to multiply the right-hand side by 1 over x. And then we're just going to distribute. So I get xy prime over x minus 2y over x equals x. And so hopefully you're comfortable with me just simplifying in this manner. All right, so now we're closer to our form. Notice that in this particular case, the a of x, so this a of x right here is the function in front of the y, but you have to include that negative. If the negative's not there, don't worry about it, but if it is, you should include it. So that means that a of x is equal to negative 1 over x. The b of x, well, that's actually the function over here. So the b of x in this case is equal to x. Now this function doesn't really play a role. It's not really important. In fact, the one that we really care about is this one. Because now what we do is we compute something called the integrating factor. And so the integrating factor, and this is why it's called the integrating factor technique. The way you compute this one is you take e to the a of x. That's what the integrating factor is. And so in our case, and I just see a mistake that I made, so I apologize. A of x, I lied. It was negative 2 over x, because I noticed I have a 2 right here. So I caught the mistake. Sorry, guys, no points. But here is how I compute this. I go e to the negative integral 2 over x. And sorry, I'm supposed to take the integral of whatever a of x is. Okay. And so I've got to do a little bit of integrations here, hence the term integrating part of the factor. So that's where the integrating part comes from, because we're going to do a little bit of integration here. So e to the negative 2, the integral of 1 over x dx. Luckily, this integral is something that you've seen many times already this semester. E to the negative 2 natural log of x. I'm not putting absolute values. I'm okay, because if you remember, x is positive, so I don't have to worry about absolute values. So I'm good. No mistake here either. Now you have to remember a little algebra, and looking at your quizzes, this is an area where we have to do a little bit of work. There is a natural log rule, so I'm going to move actually over this way, that says the following. This is something that you should have seen when you were in high school again, or in pre-calc. When you have a number in front of the natural log, you can bring the number to the inside. I'm going to use that right now. Here, this is the natural log of x minus to the negative 2. On your quiz, a lot of you guys didn't remember that trick, and you lost some points. And so now this is equal to x minus 2. This part you guys sort of do remember. Or if you want, 1 over x squared. All right, so now you compute the integrating factor. So now we go back to my equation, my differential equation. We have, and let me rewrite it because it looks ugly now, but I have y prime minus 2 over x, y equals x. Now the word factor usually implies multiplication, and that's exactly what we're going to do. We're going to multiply both sides by 1 over x squared. And so now we're going to get 1 over x squared, y prime, minus 2 over x cubed, y is equal to 1 over x. And then here is the most amazing part of the trick, at least for me. I think this is kind of the cool part. This left-hand side is actually a derivative of a function. And this is the part that makes this trick so useful. It's actually the derivative of the function 1 over x squared times y. And this, you've seen this type of notation before. You should have seen it again in Calc 1 when you did implicit differentiation. And so I'm going to show you on the side again. So this right-hand side is all my scratch work. But I want to show you on the side again why this is true. So this is going back to Calc 1. Like I said, this class, the reason it's hard, we go back to everything we've learned. But you guys are smart. You guys will get this. So implicit differentiation means first you take the derivative of 1 over x squared times y plus 1 over x squared, and then you take the derivative of y. You're basically using the product rule. The derivative of 1 over x squared is actually negative 2 over x cubed. I'm going a little fast because I know you can pause the video and you should be able to compute that derivative yourself. I'm going to use the commutative property of addition. Oh, that wonderful property we keep seeing. I'm going to reverse the addition. And now look at what I just wrote. I wrote 1 over x squared y prime minus 2 over x cubed. That's exactly what I had over here in blue. And I said these two things were equal. And because they're equal, we can use substitution. This is why the equal sign is so important to me. All right, now we're going to use the fundamental theorem of calculus, because now I can take the integral of the left and it has to be with respect to dx because y is a function of x. It's a function of x. It's an implicit function of x. And then on the right, we're going to take the antiderivative of 1 over x dx. And so there they are. They're my both integrals. And then the nice thing is that the fundamental theorem of calculus says that when you take an integral and a derivative, they're opposites. So you're just going to get back the function in the middle. So you're just going to get on the left 1 over x squared y. And on the right, you're going to get the natural log of x plus c. And again, I don't need the absolute values because x is positive. So I solve for y. So y equals x squared, natural log of x, plus cx squared. I just multiply both sides by the 1 by x squared. And now I'm almost done. The last part is I need to use my initial condition. Remember that y of 1 is equal to 7, so now we go to this last part. Again, here, I want to use the fact that y of 1 is equal to 7. So I replace the y with 7. I replace the x with 1. By now, I think I've given you enough problems that you know the natural log of 1 is 0. And so I get 7 equals c. And so my last answer is that y equals x squared, natural log of x, plus 7x squared. Alright, I hope this video helps with your interest cards. You have two problems that are similar to this. There's a lot of work involved, but again, you guys are smart. You guys can figure this out, so good luck.